They tend to be.
It's really that simple. Looking at the data, he was wise enough to understand that there were, really strong contradictions in the data, and he simply showed us by detailed, clever analysis that um, the problem was really with the lack of resolution in the ocean component of the model, and that's a beautiful example of um, the way in which his take on the way the climate system works has delivered really important insights. So today he's going to talk to us about cold climates and continuing with this 2 for the price of 1 structure of all of his lectures this week. He's going to talk about more recent glacial conditions and also cold conditions elsewhere in our solar system. So please join me in welcoming Kelly again.
Thanks. Thank you. Can you hear me okay in the back with the microphone and everything? Great. Actually shifted the balance a little bit. So instead of glacial cycles, I decided to talk about snowball Earth and Europa's ice. So let's see what you see here. And so this is the work with my very, very long time collaborator, Yossi Ashkenazi. So this is snowball Earth. You know, you see the Earth freezing gradually and then exiting snowball Earth. We'll talk about when that happened and so on. And then this is Europa, the moon of Jupiter. So I'm hoping to talk about both different elements of that. So we've done work on this for the last 10 plus years. Let's start with snowball. So let's see, what do we see? So this happened during the Neoproterozoic. So it's this period of 1 billion to 500 million years ago. There were 2 events of complete glaciation of the ocean. And at the time, the sun was 7% weaker. The ice cover over the ocean is estimated to have been 1 kilometer thick. So the ocean was covered with 1 kilometer thick. You know that sea ice is typically 1 or 2 meters. And there was another kilometer of seawater deposited as ice over the continent. So the ocean, instead of being 4 kilometers deep, it was only 2 kilometers deep. So a very different ocean. And the evidence for that sort of thing is you go and you find things like that. So this is called the dropstone. You can see that this is a small one, but there are also big ones. And that happens, and you see that the dropstone is falling into layers of sediments that are basically dust that settled on the surface of the ocean and sank to the bottom. And a dropstone like that basically means that this stone was embedded in some ice, and the ice floated to the middle of the ocean, melted, and dropped the stone. So that tells us that there was ice. Okay. In addition to that, you can then use magnetic evidence all over the world. And when you see a point that is red here, so these points right here and here over there, so that means that 500 million years ago, these points that have dropstones were close to the equator. Long story, I have to find this out. So we have evidence that these places, because of continental migration and so on, were at the equator and have dropstones. So this tells us that there was ice at the equator, and from that we conclude that there was ice everywhere. That's the evidence for these snowball events. Make sense? Questions? Yes. This is the standard evolution of stars like our sun, is that they get weaker. Over this time scale, so this isn't a direct evidence, but you can observe many suns like ours, and you can see the evolution of a standard sun. And from that, we conclude that it was about 7% weaker. I think that's something well established. And then let's see what else. Okay, so what are the open questions? How did this start? How did life survive? So the only life at the time were basically unicellular life, mostly bacteria. But how did these bacteria, some of which were performing photosynthesis, how did they survive under a kilometer of ice, right, is the question. And of course, for us, the big question was, what is the ocean circulation in such an ocean, just for curiosity, but also has some geochemistry applications. Great. So that's the question we're asking. What would the ocean circulation look like under a kilometer of ice in an ocean that's only 2 kilometers deep instead of 4? So we know we run a model, and the model is forced by two things are forcing such an ocean. There's no wind forcing, but there's surface temperature that you could estimate using energy balance considerations. So the temperature in the equator is minus 30 degrees at the surface, and the temperature at the high latitudes is even colder. So that's one forcing. The temperature gradient at the top of the ice, which is 1 kilometer removed from the ocean itself. And then there's geothermal heat flux that are very, very weak, but also are enhanced over mid-ocean ridges. So we have to take that account. You can't just apply a uniform heat flux at the bottom. You have to use some ridge, and over the ridge, the heat flux is induced. But these are the only forcing. There's no wind and so on. So the expectation was that the ocean would be very quiet, very quiescent, but it turns out that that's not the case, as you'll see. So what do we see? Let's start with what we find, and then we'll try to explain why. So here's the temperature. So the first thing you see, what you see here is latitude from the South Pole to the North Pole. This is a two-dimensional model. We also did three-dimensional and so on and so forth. This is the depth, and this is the ice layer at the top. So you see, first of all, from this color bar, that the temperature range is very, very small. So half a degree is the maximum range of temperatures you get. And the freezing temperature, because the ocean is covered by a whole kilometer of ice, the freezing temperature is suppressed because of the pressure effect of the ice on top. And in addition to that, the ocean is very well mixed. You can see vertically and horizontally. So if you have some chemistry happening anywhere, it's going to be well mixed. Again, that's important for some of the geochemical evidence. Won't get into that too much. Okay, so what do we see? Small temperature gradient and well-mixed ocean. This is the salinity. It turns out that you get freshening here. The reason for the freshening, so you can see that it's, again, that the gradients are small of salinity, but you get freshening here because this warm temperature melts the ice here. So you get melting of ice here and freezing of ice in the high latitudes. And that leads to these salinity gradients. The melting and freezing lead to salinity gradients. There's also an ice flow, which we analyzed in different papers. So and the density gradients, which control the currents, are dominated by salinity, not by temperature. The effects of salinity on the density is negligible. Sorry, the effects of the temperature on the density is negligible relative to the effects of salinity. So as far as the density is concerned, and thermal wind and so on, the main effect is salinity. Questions? Okay. And then we find velocity. So first, there's a strong jet. This is the latitude again. So there's a strong zonal jet at the equator. You can see a double jet with different signs. And the overturning is really interesting. Look at the overturning. I mean, the overturning is restricted to the equator only from -5 degrees to +5 degrees. When we got that for months, we were convinced that there's actually a bug in the code somewhere. This is the MIT GCM. How could the overturning look like that? So a big part of this would be to explain why the overturning looks like this. So here's the overturning again. Just to remind you, this is the present day overturning. So it's, you have water flowing all the way to the North Atlantic, sinking, coming back. But in this case, the whole overturning happens just at the equator itself and nowhere else, right? So that was a big puzzle. And again, as long as you don't have an dynamical explanation for this, you can be sure that this isn't some bug in something in the code. You're running the ocean model in a situation that it never saw before, obviously. So that was a bit strange. So in this case, my collaborator Yossi was able to figure this out. So what he did is the following. You write the momentum equations. You identify only the terms that are important. And these terms are highlighted in blue. So even though the MIT GCM has all of these terms, you have one viscosity term that's important, Coriolis form. In this other one, it's basically geostrophic and then hydrostatic. And you remember that F around the equator is just equal to beta Y. And turns out you could actually derive a simple scaling for that, where U would be proportional to 1 over Y, and V goes like 1 over Y to the fourth. So V is the overturning circulation, and it decays rapidly according to a scaling you derive directly from the equation. And that explains why we saw what we saw, and that reassures us that it's not a bug and so on. So, I mean, the details are a little bit complicated, but to go from here to this is very straightforward. Okay, so we have very strange overturning that can be explained from using dynamical reasonings. Okay. Great. Then we moved on to three-dimensional just to see what happens. Yes, Eric. Yeah. I mean, the only way because the wind can't affect the ocean through a kilometer of ice, the only effect is the surface temperature distribution at the top of the ice, which affects the fluxes through the ice, the diffusive flux that escapes from the ocean or goes into the ocean. So that is one of the forcings. It's basically a meridional temperature gradient at the top of the ice. That is the only thing that the atmosphere does, basically. I see. Yeah, okay. Yeah. Yeah, I think that overturning circulation would have existed even with a flat atmospheric profile, but you need something. So you need the geothermal heat flux or something to drive this. But yeah, it doesn't depend on that gradient. Yeah. Okay. So in the three-dimensional version, you look at, so this is a spherical land mass that we put at the center here so that it won't be an aquaplanet because there were continents even in the case of snowballs. It's obviously super idealized and we're only showing the equatorial section from these integrations. So this is our land and you see that the temperature is super turbulent, right? So even though the only forcing is like 0.1 watts per meter square from the bottom and a bit of flux from the top through a whole kilometer of ice, that's a very insulating quantity. The ocean ends up being very turbulent, and the salinity also shows this turbulence. And the zonal velocity shows these interesting zonal jets. And the overturning in this three-dimensional thing looks exactly as it did in the two-dimensional thing that we looked at before. So this is reassuring that even when you have eddies and waves and so on, which we didn't have in the two-dimensional model before, you still get the same overturning at the equator. So that's, again, reassuring that maybe it wasn't just a bug. But the jets here are interesting, and they will also be important when we get to the Europa story. Okay. Exactly. Yeah, it's surprising. Yeah.
Is it angular momentum conserving? Is it that kind of dynamic? Help out under ice how they sell?
I mean, in this case, you talk about PV conserving rather than, but it's the same difference basically, right? When we get to Europa, angular momentum actually becomes an issue, and I'll talk about that just a little bit. So if you see vorticity and PV as angular momentum, yes, it's conserving. Is that what you meant basically?
What the role of the viscosity in the earlier model.
Yeah, I mean,
What setting that radion scale.
I see. Right. I think when we analyzed the distance between these jets, it ended up being proportional to the viscosity, the eddy viscosity you calculate from the turbulent properties of the fluid. So eddy viscosity does play a role. So you're resolving eddies, you could estimate eddy viscosity from that, and using the eddy viscosity, you can get a scale for the separation between the jets, and it seems like it's playing some role. Okay, so to summarize this part about the snowball ocean circulation, so we find this very funny overturning circulation, and the ocean is very well mixed everywhere. So, one of the evidences that they find is something called banded iron formation. So this is something that exists, that is formed only when there's no oxygen and so on. So if the ocean is well mixed and you have some opening here, you wonder whether banded iron formations can form if the ocean is open. So you've done some work on the ocean being not completely, I don't know if you saw a recent paper about that. So recently we showed that even when you have opening at the surface, if you run a geochemistry model, his student did that, Kaushal, then you can still form banded iron formations even when the surface is open. So I thought you might be interested in that. Yeah. Anyway, so I think the whole ocean mixing thing is relevant to some of the geochemical evidence and so on. Maybe I shouldn't get too much into this. And we found it to be surprisingly turbulent and energetic in spite of the fact that it's such a small forcing. Right? So dramatically different from present day, obviously. Not stagnant as was assumed in many geochemistry papers before, well mixed horizontally and vertically, and in this equatorial meridional overturning circulation. Okay, any questions about this part one? Yes.
Is the position of the equatorial like overturning depend on it being close to where that like ridge is, or is it only because it's that like y1 over y to the 4 dependence? Like could there be some with y minus whatever the latitude of
Yeah.
the.
I'm gonna have to guess, but I'm guessing that if you move it a little bit, it would still be at the equator because these dynamics that we talked about are sort of, and also in the three-dimensional models that we've run, some of them have more realistic snowball time blend geometry, you still get that sort of thing. So I think it doesn't depend on where the ridge is and so on. Like, but if you move the ridge to the other side, the sense of the orientation of the MOC will reverse actually. So the orientation, the sense of the circulation, they being in this direction, that's going to be a function of where the heating is. So
Ellie,
The-
what's the logic that gets you to an ocean with mean depth of 2 kilometers rather than 4+?
okay, so the ocean today is 4 kilometers deep. 1 kilometer is frozen, so that brings you to 3. And then the estimate is that 1 more kilometer of seawater was deposited over land as ice, and therefore what's left is only 2. That's an estimate. There's no direct evidence, obviously.
But that could be critical.
If the ocean were 3 kilometers instead of 2, maybe that would have made a difference. I don't actually know because we didn't try that. Great. More? Okay. Great. Okay, I think that was number 1. Then we have number 2. So let's see. I think the number 2 is this one. So same collaborator, Yossi. We've been working together for over 20 years. And this time the question we're asking is different. It has to do with the ice shell of Europa. So this is what Europa looks like. Pretty impressive. So this is the moon of Jupiter, right? Okay, what do we know about it? So first of all, here's Jupiter and 2 of its moons, 2 of the Galilean moons, if you want. One of them is, the left is Europa, and what is it? Io on the left and Europa on the right. So this is Europa and this is Io. You see them on the background of the red spot here. Pretty dramatic picture, isn't it? I mean, this isn't ChatGPT, this is a real picture. And this is what Europa looks like itself. And if so, Europa looks like this. So its radius is 1,500 kilometers. So it's smaller than our moon. Gravity is about 10 times weaker than on Earth. And there's an ocean that's estimated to be 100 kilometers deep. Okay, so very, very deep ocean. We got into Europa because we said, okay, well, we worked on this snowball. What could be simpler? Let's just apply it all to Europa. It ends up being a totally different mess, and we got in trouble for it. But happy end. So 100 kilometers of water, and the top is frozen. What the thickness of the ice that's frozen is not clear. This is now model estimates and so on. So between 10 and 50 kilometers, maybe. Let's call it 20 just for the fun of it, but we don't know exactly. But we do know that it's about 100 kilometers of ice and water. That's based on the mass of Europa and its size. And so you can calculate. And if you assume that the center is rocky, then you can figure out that about 100 kilometers is going to be water. And this is what the surface looks like. People refer to this as the chaos terrain. This is what the surface looks like. Super dramatic again, isn't it? Just beautiful. Okay. Okay, so now what is the problem we're trying to solve when it comes to Europa, right? So you see craters on Europa. Actually, these are craters these are the craters on Europa, and they're different sizes. So you can see the scale at the bottom. So they're different sizes, but the interesting thing is Europa is phase locked to Jupiter. That is the same phase of Europa always faces Jupiter, just like our moon is always facing the same side of the moon, always facing us, right? So you'd expect maybe that the fact that one side always faces Jupiter would mean that you'd have more craters on one side than on another, because some of it is protected by Jupiter and so on. But it turns out that the crater distribution is more or less uniform. So you wonder whether the icy shell is actually moving around. So even though it's phase locked, that is always the same face of Europa facing Jupiter, maybe the ice is slowly rotating, even if the rocky part is always facing the same side of the rocky part, the rocky interior faces Jupiter, maybe the icy shell is rotating, and that might explain over a few millions of years in which this ice cover exists. Maybe that would explain why the crater distribution is uniform. So we're looking for a mechanism that would make the icy shell rotate. And the mechanism will be that the ocean currents push the ice, because we've calculated the ocean currents. It has to have some applications. So we assume that the ocean currents that we calculated affect the icy shell and move it around. That's where we're coming into this. Any questions about the question? Yes. Yeah. Yeah. Yeah, I mean, I think one difference is maybe that the ice cover of Europa is not that old. It's estimated to be, I think, tens of millions. I'm a bit on thin ice here when I say that. I'm not completely sure. So that makes a difference, right? If you have 4 billion years or you have just a few tens of millions of years, I think that makes a difference in terms of the crater coverage. Yeah. Okay. More questions about the question? Okay. So this summarizes it. So it's phase lock to Jupiter. By phase lock, we mean same phase always phases. So we expect some asymmetry in the crater distribution, but it's not there. So the question is why. So, okay, so I'm just showing one slide from a previous paper in which we analyzed Europa's ocean. So this is the circulation we find for Europa. So this is the depth of Europa's ocean. And this is latitude going from the South Pole to the North Pole. And you see this zonal velocity that develops, a jet that develops at the equator of Europa. There's a strong jet that develops. And if you look at the circulation in a three-dimensional model and so on, you see it being turbulent again and so on. So same thing as in Snowball, even though this is under 20 kilometers of ice this time, and even though there's just weak geothermal heat flux in Europa, you still get a very dynamic, very turbulent ocean with a strong jet at the surface. So we're counting on this jet to apply torque to the ice and move it around. That's how this works. Make sense? Okay, so without getting into the dynamics of the ocean itself, let's jump directly to this. So here's what the geometry, so we built a simple model for the rotation of the icy shell, taking into account the torque that the ocean circulation applies. So here's Jupiter, very big, Europa, much smaller than this, so it's not to scale. And because of tidal forces applied by Jupiter, Europa is going to be elongated. So I exaggerated this angle between the elongated shape and Jupiter. It's actually, this angle is basically very, very close to zero. But just to make it clear what happens, so there's this elliptic shape that's basically oriented toward Jupiter because of the tidal forces by Jupiter. Okay. And then the forces and then you look at so you're looking at Europa from above. So this line is the equator of Europa. And suppose there's a crater on the equator of Europa right here, and we are following that crater location. So it's a Lagrangian measure of the location of the icy shell and how it moves around. And the forces that act, as there's going to be an ocean torque because of this zonal jet in the ocean at the equator that will try to make the icy shell go around. And then there's an elastic force, complicated story that tries to restore it back. So I want to show you one slide with the mechanism of how we think the icy shell would rotate due to viscoelastic adjustment. Okay, so that's the next slide. And then I'll go into the details of the simple mathematical model. So here's the mechanism. So suppose we start at t equals 0. This crater is just facing Jupiter. But there is a torque by the ocean that's trying to rotate the icy shell of Europa. So at the next moment, we'll find that the ellipse is shifted, and you see the crater that was at the peak of the ellipse is now shifted from the equator. Now the icy shell is viscoelastic. So if you put it in this state, you have the tidal forces that keep affecting it. So it would slowly distort back such that the part facing Jupiter would be elongated, but the crater itself would remain off the equator. So after enough time, if you let the ice adjust viscoelastically, It restores the elliptic shape facing Jupiter, but now the crater is here. And then this would happen again and again. So the crater moves around, and this indicates that the icy shell gradually goes around. Okay. I think it's really important that we understand this before I get into any equations, because they're not important. I think this story is what's important. So please ask me if it's. Does this involve a lot of? Yeah, it must involve some cracking, I would assume, because you know, the ice on Europa. It's important to understand the outer part of Europa is at such a temperature that the ice is as hard as granite. Okay, the lower part of the ice that's bordering with the ocean is soft because it's, you know, close to the freezing temperature. So when you distort it, some parts of it must crack, absolutely. And how that affects, I don't know. I mean, yeah, but yeah, there has to be cracks. Should I repeat this explanation? Do you mind if let me repeat it? Okay, so here we go. So 3 steps that explain how a crater that starts facing Jupiter finds itself here. Okay, step number 1, you have this crater facing Jupiter, and now the ocean torque, the ocean currents on the equator of the ocean, try to push this icy shell around. So then it, oops, what's that? So then the icy shell finds itself in this position with the crater and everything. Okay, so now that the ellipse is shaped in this direction, the Jupiter tidal forces want the ellipse to look like that. So the icy shell, the crater is here, but now the ice is slowly distorting to conform with the direction of the Jupiter tidal forces. So the ice has to distort. And as it's distorting to go back to this shape, the crater location remains off this line between Jupiter and Europa. So, and then this repeats again and again and again, and the crater will be moving around, and therefore the meteorites that hit it would cover the entire thing. That's the story. So now the question is this. We have some evidence. There are 2 snapshots that were taken of Europa. I forget how many years apart, roughly 20 years apart, not exactly 20, by 2 different missions. So this gives us some estimate of how rapidly the Europa is rotating. And basically, we know that it's very slow because the 2 snapshots are actually very similar. So the question is, if we take the currents that we calculate from the ocean model, how different is the rotation rate from the observational constraint? Yeah. Yes, so there's the Europa core. So remember, there's a rocky core that's most of the thing, and then there's a 100-kilometer ocean, and then there's an ice over that. So the core always faces Jupiter in the same direction. It's only the icy shell that moves around. Sorry, good.
The combination of these effects kind of rotates the axis.
Right, yeah, so this would be the axis of rotation of Europa, and it would be spinning like that. Think about this as the North Pole facing us. Okay, so I look at the time and I see that it's not important that I go through the equations and all that, because we talked with the students last night that I wanted to mention something else due to that. Let's just directly to this. I mean, the model does what you tell it to do. There's a parameter that has to do with the viscosity of the ice and so on, and you could use the constraint on the rotation rate of the ice to constrain the viscosity, but it's very technical, and I would be boring if we did that. So the idea was to explain the crater coverage on Europa's shell. So we developed this simple model, which is basically a harmonic oscillator-like model, and we have a torque due to the ocean forces. And we have some observational constraint on the drift velocity, and this tells us how rapid the viscoelastic adjustment is and so on. That's fine. Okay. Thank you.
the jet you showed is really confined to the equator, so, is there a differential rotation of the craters, because there's less of the ice is not.
Yeah. So because the outside part of the shell is so hard, you expect the icy shell to actually move. Yeah. Although the lower part of the ice is soft and it actually flows, and we modeled that ice flow as a shallow ice approximation type of thing in a different paper. So the ice flows, but not the outside part of Europa because it's so hard. Yeah, you assume that the net torque applies to the entire icy shell and it moves as one solid object. Great, so that was number 2. And I think, so we had the chat 11:43. So we had the chat over dinner last night and geoengineering came up. Do you guys mind if I give you my spiel about geoengineering? Okay. Do we have any supporters of geoengineering here? Solar geoengineering. Okay. Hopefully I'm not going to offend anyone.
Breaking the symmetry of two.
That's right. It's symmetry breaking, exactly. Okay. So let's see, we should get rid of this one too. So these are the problems that people mention when you talk about, so everyone knows about solar geoengineering, right? The idea is you put sulfate aerosols or some other, now people talk about diamond dust into the stratosphere, and this reflects some sunlight, and all you need to do is reflect 1% of sunlight to compensate for doubling of CO2. So I mean, it really does sound like a wonderful idea. So what are the problems? So of course, ocean acidification is one, because if CO2 keeps rising, even if you compensate for the warming, the oceans still keep getting acidic. And you know that the concentration of H+ ions in the oceans already increased by 25%, right? You know that. And by, pH is a log scale and all that, so that explains it. So ocean acidification is one problem. People mention problems with the hydrological cycle. You change the shortwave radiation, that has to have some effect. So maybe, for example, Ethiopian famine caused by volcanic emission that also emits sulfate aerosols and so on. Ozone depletion is something people mention, particularly for sulfate aerosols, but then people come up with other solutions. Again, the calcium carbonate or diamond dust and things like that. So maybe that will have a solution. Whitening of the sky, if you like to look at the sky, it won't look the same, but our grandchildren won't know about this because they'll be used to that. So maybe that doesn't matter. Acid rain, I think that's a small constraint, the small issue, because the amount of sulfate aerosols is actually not that large that you need to put into the stratosphere. Unknown ecological consequences. Hertz solar photovoltaic. Okay, well, 1%, no big deal, right? Okay, so I'm actually not worrying about any of those. So let me tell you what I think is the problem. And people think about it as the moral hazard. It's not that I have something very, very new to tell you, right? It's just a version of the moral hazard. So what is the moral hazard? It's the idea that if you now have this solution of sulfate aerosols or some other aerosols in the stratosphere, that you don't have as much motivation to reduce emissions. And therefore, it will keep building up more and more CO2 in the atmosphere, and will keep building up more and more sulfate aerosols or some other aerosols. And now you have these two large forces that have, so now it's not going to be just 1% of short wave, maybe 3%. It's becoming significant, and 2 or 3 doublings of CO2. Maybe that's a reason to be concerned. So suppose you have this new situation of high CO2 and high sulfate aerosols or other aerosols concentration in the stratosphere. And at that point, you have, 1,500 ppm of CO2 in the atmosphere. And then you finally discovered that, okay, well, maybe it wasn't a good idea, because now you have more cyclones hitting Bangladesh and people are dying. And what do you do then? Because the idea about solar geoengineering was that you can always stop it, and within a year and a half, all these aerosols would fall out of the stratosphere. It's no big deal. But what if this is discovered only when the CO2 is already 1,000 ppm? Then it's going to be a problem. And then if you stop geoengineering, you have this abrupt termination shock that people worry about. But I think the other problem, so my variant of this moral hazard is that you know, you have strong geoengineering and you have high CO2 and you're trying to balance the two. This is meant to explain to people what instability is, but you all know what instability is. So you might have a system that becomes unstable. You know, two large balancing forces is a recipe for instability. And the instability could mean that something might happen at that point that can't be anticipated, right? That's sort of the problem. So I think often you think about this as we have CO2, that's a bad thing, but we balance it with geoengineering. So, you know, thorns and roses, everything is fine. But maybe that's not the way to think about it, because once you have lots of CO2 and lots of geoengineering, it might look more like this. This is from ChatGPT image generator. Isn't that amazing? You can go and ask it to plot two elephants on a scale. So when you have something like that, you could, you know, you're breaking the climate system. You see the scale is the climate system and you're breaking it. And I think that really is would be my concern. Okay. So I think the issue is that SRM might give us a false sense of security, and then we stop emitting CO2 again. People refer to that as the moral hazard, and then that plus the instability is a problem. Okay, why did I stop worrying about it? Does anyone have any comments at this point? Yes. Are you a believer in geoengineering?
Impact of deep convection at the TLS and its ability to potentially scavenge and sort of the same kind of faster than we think. And so that's not going to be in any climate models. So what do you think about that?
Yeah, so I mean, I think all the research that people are doing is based on models. We know that models have their limitations. So if we think we're figuring out all the dangers, we're probably not. Absolutely. So why did I stop worrying about it? Because if you need to have a successful solar radiation management project, you need an international effort that would coordinate. Of course, it's possible for some billionaire to decide that they do it. All you need is 50 Boeing planes and a few billions of dollars per year. And we know some individuals who are capable of doing that, right? But you would think that it would be an international effort and so on. And we don't really have an international organization who is capable of managing something like that. So I'm optimistic that because we're so messy as humanity, we won't be able to do this. And I decided not to worry about it. That's my version. The doors will fall out and great. Anyone has comments about solar engineering, solar geoengineering?
So the love part is not clear. Stop worrying about it, but probably don't.
Obviously not love, yeah. It's just an obvious reference, you know. But everyone understands the reference about loving the bomb and all that. Right, okay, great. Okay, I think that's it. Okay, so I wanted to spend a few minutes just summarizing everything that we did this week, so we can get rid of all of these. It's only the fourth presentation for today. So just because there was so much stuff and all, I just wanted to sort of review everything very, very briefly on a very high level and sort of remind you. So we talked about different climate surprises, warm, cold, past, and future. I learned to say U of T. That was my exercise for the week. So we talked about 5 different things, just reviewing them. So the first one was the wet California and the anthropogenic, the attribution, right? So the first was that I mentioned that California was very wet 2 to 5 million years ago in a period that had a CO2 concentration that was about 400 ppm, and that might have happened due to some interaction of the hydrological cycle over California with upwelling. This is the upwelling over near California, and you can see the cold water here. So we suggested a feedback in which this cold water warms and the land becomes water and so on and so forth. And I explained that this doesn't happen in climate models because currently they can't simulate the upwelling properly. And then the second half had to do with attributing extreme events. So these are the extreme events, and you have a PDF for extreme events, say for heat waves, and the PDF shifts so that something that was very unlikely to happen on the tail here becomes much more likely. And can you use this statistically to attribute specific events to global warming and so on? And we talked about that. So this is the work of Min Fu, and this is Peter Sherman. Oh, okay. Yeah, great. So, and this reminded me that I actually wanted to explain why paleoclimate is interesting and fun. Okay, so this is an argument. So suppose you know what the temperature looks like. So this is the hockey stick, right? You have the temperature maybe even cooling over the last 1,000 years and then obviously warming. And this is just 1860 to 2000. And you can see the hiatus that we had from 1940 to 1980. The temperature looked like this, right? So there's the general warming, but there was this period in which there wasn't warming. So suppose we are climate scientists now and we live in 1980. And we don't know very much about the past because we didn't learn to be interested in paleoclimate. Well, so all we know is the recent past. So what we see is this. What do we see? Mike?
Nothing, maybe a decline.
Maybe a decline. We're seeing cooling, not warming, right? Yeah, so people saw the cooling and they got concerned because of the cooling. You know about this, right? And what would you do if you see cooling? If you're a serious scientist? You write a letter to the president, right? So here's the letter that was written to the president, Nixon at the time. So let's see. Dear Mr. President, this is 1972, and the concern is the cooling. So we say, aware of your deep concern with the future of the world. Perspective now, I don't know anyway, but yeah, so we feel obliged to inform you of the results of a scientific conference. And in that scientific conference, we find that a global deterioration of climate by orders of magnitude larger than any hitherto experienced by civilization, mankind, is a real possibility. Now, they're not talking about global warming, they're talking about global cooling. Would you raise your hand if you've seen this letter before? Oh, great, excellent, excellent. So the cooling has natural causes and falls within the rank of processes that produced the last ice age. So basically, they're concerned that the last ice age might come again. I think this is, the people understood that aerosols have a cooling effect, and then they were concerned that that would kick the Earth into a new snowball, right? Okay, so what would be the results of that? So they first say the present rate of cooling is fast enough to bring glacial temperatures in about a century, okay? Great, what would be the results? So first of all, substantially lowered food production and increased frequency and magnitude of extreme events. Does this sound familiar? So I think that's a lesson for us, right? Yeah. Okay, well, how do you convince the president to actually do something about this, though?
It's gonna cost money. It's gonna cost money.
That's a reason not to do anything, but you're saying these damages would cost money.
Yeah.
But I mean, that would happen after his administration, so I mean. 1970s, that's the hint. What you need to convince the president to do something, 1970s?
The Russians.
Someone said the Russians. Let's see. So we hope that your administration will take decisive steps. And as we said, the way to convince the president is that the Soviet Union, with large scientific teams monitoring the climate, so the Russians are already working on it. So the Russians are coming. Have you seen? So well done, well done. You should go into politics. Great. Anyway, I think that the lesson is obvious. You want to understand paleoclimate because it's it's useful to know what happened in the past. It gives you some perspective, and it's also fun, I would think. Okay, so reviewing the rest of the lectures. So we talked about well, yes, please. Who signed the letter? A group of very distinguished climate scientists from Brown University and others. Yeah, I obviously deleted the names on purpose, but I have the original if you want with the signatures. Okay, so we talked about Arctic air formation in the present day climate, and we talked about the fact that the same area, say Wyoming, was nice and warm and pleasant 50 million years ago. And to explain that, we came up with two cloud feedbacks. One was low clouds, so basically fog over the continent, and the other one was these convective clouds over the Arctic, and together they keep the Arctic ice free and warm the continent, and that's how we tried to explain this. And this is the work of Tim Cronin and Dorian Abbott as a postdoc and student years ago. And the next one was we talked about internal waves and nonlinear wave-wave interaction that is important for ocean mixing and drives the overturning circulation. So there was we talked about that. And then we talked about the question, what makes the ocean stratification be so exponential in the mid-depth between 1 kilometer and 3 kilometers? And this was the work. So this is Golan Bell, my collaborator. And this is Madeleine, who was a postdoc, and Xiaoting, who was a PhD student. So you can see the stratification being so exponential, and we talked about what could lead to that. And then yesterday was the interaction between the Madden-Julian oscillations in the tropics, in the troposphere, and sudden stratospheric warming events. And maybe, as predicted by Waning in her PhD thesis, maybe when the MJO gets stronger in a warmer climate, there would be more of these sudden stratospheric warmings. And then this is a student who just graduated last week or 2 weeks ago, Kara, and we're trying to look for statistical evidence for a connection, a downward connection between the stratosphere and the surface using maximum covariance analysis, and didn't succeed. And Paul reassured us that that's okay because it doesn't exist. And then we talked today about Snowball and Europa, work with my collaborator this. All right. So we discussed climate change, but I want to remind everyone not to forget the good news. You all know about the horses now. And also, in addition to the horses, so I didn't show that yesterday, but the price of solar energy went down from $80 to $0.3. That's a pretty significant decline over a few decades. Things normally get more expensive, just to remind you, right? And then wind energy goes down dramatically. So there's good news. So things are getting better. So we want to remain optimistic. And I wanted to thank you very much for the visit. Great. Thank you. So, I mean, everyone was so welcoming, and I had a great time, and it was very stimulating. And I wanted to thank both the faculty for their hospitality and the students for organizing everything and all the lunches and everything. I had a great time. And thank you especially for making sure the water is so good.
All right, yeah, so before we finish, I just wanted to express a small token of our appreciation for coming here. So we have a framed copy of the poster for the week for you to take with you. Oh, someone's tripped on the wire there. So yeah, just thank you again very much for coming. I'd also like to thank the other members of the Noble committee. So could everyone that's here just stand so I don't forget anybody as I go through everybody's names. But yeah, so this committee organizes not only this week of Noble lectures, but also all the Noble seminars that we have throughout the year. And everybody contributed to organizing this week of events, from things like booking the food and catering to organizing the pub night and everything like that. So yeah, Michael Horachua, I'm sorry if I butchered your last name, John Paul Master Giacomo, Feng Yixi, Victoria Flood, Zixuan Zhao, Aaron Atkinson. I think also Petra is not here at the moment, but that's okay. And then, of course, our faculty advisors, Dylan Jones and Nico Grisward. So let's give a hand to everybody on the committee. Fantastic. Yeah. Oh, one more thing. Was it your idea last night that we take a photo with everybody? I don't know. It was somebody's idea. Do you have the camera? No? Oh, that's okay. We can use my phone. But yeah, would you stand and we can take a photo with you in the audience all in the background? Sure, yeah. Do you guys want to move over? Wonderful. All right, thanks, everybody. Remember to take all your garbage and everything with you when you leave. Thank you.
Thanks so much.
No problem.
Great fun.
Yeah, it's fantastic.
Pardon?
So great to see you here.
Great.
Yeah.
Oh, right, I forgot.
Look
See you
forward
around
to seeing you
next
next
time.
time. Yeah.
Beijing.
Oh, he was online. Okay. Well,
Oh, these are fantastic letters. Thank
Right,
you so
thank you.
much.
Really enjoyed it, obviously.
We're going to mail this to Harvard for you. Is that, would you
I could
prefer
put
that?
it in my suit.
Okay, excellent, okay.
It's not that big. Great.
So this afternoon, Nico and I have another PhD qualifying exam
Good for you.
from 2 to 4, so we will miss you.
That's okay.
But you have your luggage with you?
Yes,
The office?
yes,
Okay.
I'll talk to Fatima and she'll help me with it.
Actually, okay, and she told me she spoke to you
That's
about the
right.
new
That's
regulations on the honorarium. I didn't
Which
realize
is good
things have
news,
changed,
yes.
so that's easier. Okay, excellent.
Exactly.